Hello, my name is Shahab Dean Mohakek. I'm the director of West Virginia University Laboratory for Engineering Application of Data Science, WVU Leeds. The paper I'm presenting today is called Frac-Hit Dynamic Modeling using AI and Machine Learning. A quick outline. I'm going to first talk about what Frac-Hit is. I'm sure you all know, but it is good to have a definition and talk about it so we all working and talking about the same thing. Then the objective of this project and this paper. Then I talk to you about the data set that we have used, the actual data set that we have used for this project. And then I talk about current industry practices in modeling frac hits and dealing with it. And how does that compare with Shale Analytics, which is the application of AI and machine learning in unconventional resources? And then I'm going to show you the results. And that would be the essence of this paper and this article. So if you plot production versus time, you can see that you get oil or hydrocarbon production and you have water production, and then when the frac hit happens, the oil and hydrocarbon production goes down and the water production goes up. It has to do with when you have the parent well and it has multiple stages of hydraulic fracturing in multiple clusters that you frac it. And as you probably all know, the way hydraulic fracturing works in a naturally fractured reservoirs, unconventional such as shale, it goes to the places that nobody really knows because nobody knows how what is the distribution of natural fracture that to a very large extent contribute to how the induced fracture expands next to the wellbore. And as you can see, this would be the oil and water production, and what you see here as the shade would be stimulated reservoir volume that for this particular parent well. And then you look at the child well, and there's a distance between them. It's called well spacing, and the child well is also hydraulically fractured at different stages while the parent well was already producing. And when that happens, then if the hydraulic fractures that is taking place in the child well comes and interacts, somehow gets involved with the already hydraulically fractured part of the parent well, then that's where the frac hit takes place. It negatively impacts operators' monthly cash flow, as the operating companies know very well. This is an example of a frac hit in a well in southwestern Pennsylvania, which produced gas and water and condensate. And until when the frac hit happened, you can see what happened to the water, what happened to the condensate, and what happened to the gas. As the number of wells in a given shale asset increases, probability of interference between the parent and child well increases significantly, and frac hit is what we're talking about here. It is defined as the impact of the frac treatment of the child well on a parent well that's happening. Frac hit usually reduces the parent well's oil and gas production and increases its water production, as we just. So with that said, what is the objective of this particular article or the project that we did? The objective is to show that the best way of modeling, predicting, mitigating, and managing frac hit is to build, history match, and validate a dynamic reservoir simulation model. The only way we do traditionally build a dynamic reservoir simulation is traditional numerical reservoir simulation. The fact is, the traditional numerical reservoir simulation will not serve this purpose. And the main reason behind it is that numerical reservoir simulation modeling of shale is overwhelmed by gross assumption and simplification that are made. And pretty much it does what you want it to do rather than it modeling the reality. It has literally nothing to do with reality, the numerical reservoir simulation traditional way of doing that in shale plays. If you have done that yourself, you know exactly what I'm talking about. If you haven't done it and you believe the numerical reservoir simulation works well, well, it works very well for conventional systems, but it doesn't work well for unconventionals. Uh, Given the fact there is the number of assumptions that you have to make and include in your numerical reservoir simulation and modeling, it's unbelievable. The best way to approach this project is to do a purely data-driven and fact-based reservoir simulation, dynamic reservoir simulation, rather than based on guesswork and assumptions and simplification. That is called dynamic shale analytics. We'll be talking about that. The dynamic shale analytics requires three steps. The first step is using the shale analytics to model, predict, mitigate, and manage Frac-Hit. And then to build a purely data-driven reservoir simulation, a fact-based reservoir simulation, not a numerical one, and then combine these two together. What I will be showing you, I will show you today that how shale analytics can model, predict, mitigate, and manage Frac-Hit, and I can show you how we can build purely data-driven reservoir simulation and history match and validate production from a shale formation. And this is what I'm going to present. What remains is how can we combine this. That's the next step that we are currently doing research and projects on, to combine these two and have a dynamic shale analytics. So let's talk about analytics. First, I'm going to talk about the traditional Frac-Hit modeling that currently is used in our industry. The current standard industry practice to predict the occurrence of Frac-Hit is mainly a function of horizontal distance between the child well and the parent well, as well as the stacking, this spacing and stacking. The parent well, of course, is pad of multiple wells is already producing, and then a child well is when you start drilling a new well and start working with it, and then the distance between them, we call it x, and the user defined cutoff distance, we call it x sub cd. And as long as the distance between the child well and the parent well, once it's less than that x cd, then Frac-Hit is going to happen. In other words, if it's more than that, then it's not going to happen. I'll explain that in more detail in a second. So originally, the way in our industry this was dealt with, where they said, okay, if the distance, the cutoff distance is true, if you are within less than your actual distance is less than cutoff distance, is that if that is true, then and if you're on plane, I'll talk about that in a second, then there is a possibility of Frac-Hit, and if you are further down from each other, then no, there is no Frac-Hit regardless of what the on plane is. So the cutoff distance is how far the parent well is from the child well. And the next one is the key on the word on plane. And if you look at parent wells with a pad that have the spacing between the wells about 1,000 feet, and then you do a child well with multiple stages of hydraulic fracturing, and these two stages, for example, 1 and 2, which is the red and the green one, are in the same plane as the production of the wells, the parent wells in the pad. And the word on plane is the parent well is within the frac plane of the stages being completed in the child well. And what you see here is what's going to cause the Frac-Hit. That's what the on plane is. And when you do that, you'll find, I mean, they did that in our industry for a long time. They found out that's hardly ever doable. And then they added another piece, and that was shielded. So that has distance, then it's a stacking. Are they in the same level as well? So let me talk about that here. Is when the shielded came to be, then not only the cutoff distance had to be true, and not only the on plane had to be true, but also it shouldn't be shielded. If it was shielded, if it was on plane, then and it was shielded, which is yes right here, then there would be no frac hit. But if it is not shielded and still on plane, and the distance is not enough, then they will be shielded. And that is what our industry uses today. Uh, and I'm going to show you the data that we have and how it works. Let's first talk about shielded and explain what shielded means. Shielded means if you have this pad that's producing with multiple parent wells, and then you have a child well that has 4 stages, and then the well that we're talking about right now is this one in the red. And the question is, does this well get frag hit as long as it's shielded by this blue well, right? So if they're in the same plane, then the chances is for the blue well to get frag hit, not the red, the well shown here by red. Why? Because it's shielded by another well, and that shielding does not allow the other one to get frag hit. And that's what currently what our industry is doing. We call it traditional Frac-Hit modeling. So as we move forward, the data set that we have used is about 1,000 cases, 959 cases. The distance between the child and parent well is from less than 1,500, between 1,500 to 2,000, and between 2,000 and 2,500. About 250 of them are in between less than 1,500, 400 of them more than 2,000, and about 300 between 1,500 and 2,000. And as you can see here, and what you see, the percent of the frag hit that you see, when the shorter the distance, the higher the percentage. As the distance goes higher, the frag hit actually percent becomes lower. And again, the same thing, as this goes higher, this goes down to 10%. This is data that we're dealing with. And if you look at it, the same data, instead of putting it in only 3 categories, I'm putting it in 20 different categories. From this is the load that we have 4 wells that have about 780 feet distance. We have 12 wells that have this amount of distance, and so forth. And then you can see what is this state of frag hit. 75% of this, 75% of this, 87% of these, 23, 63% of these. And as you see, as the distance goes high, the percent of frag hit goes low. And so it's less than 1,500. You see very, very high amount of frag hit. And this is the most important one. Why? Because this is usually what companies would like to do. In order to produce more oil, there has to be distance be shorter between frag and child, parent and child well. And of course, between 2,000 to 1,500 to 2,000, you can see it's about 30 to 40%, 30 to 40%, and above that, it's about 10%. So let's look at the data that we have. How much of them are on plane? About 300 and about 400 of them not on the same plane, and 566 are. This is the total. And when it comes to shielded, about 58% are not shielded, and 42% are shielded. These are the actual data that we're talking about about on plane and shielded. There are 4 possibilities: being on plane and not being on plane, being shielded and not being shielded. And these are the percentages. So the data that we have, about 31% of it is on plane, but it's not shielded. This is what happens most of the time. And here's the rest. So actually you can see that highest possibility of actual frag hit is when you're on plane, but you're not shielded. And that is the mostly happening and the toughest part that we're dealing with. So the FracHit for the actual field data that we are dealing with, as you can see, this is where it happens most. You have 103 of them are a no hit and 196 of them are FracHit, or 34% no hit happens, and about 66% of them we do have FracHit happen. This is where, as I said, happens mostly, is highest possibility, and we deal with it more than any other. The other ones that you can see, it's 82% not get FracHit and 17.6% does get FracHit. When there is shielded and it's not on plane, the amount is much lower, the FracHit, and not FracHit is a lot higher. And of course, furthermore, when it's not on plane and it's not shielded, again, you get a lot less FracHit than you get not not FracHit. And now let's look at this is the actual field data. As you can see, when it's on plane and shielded, this is the percent of FracHit, it's about 17%. When it's on plane but it's not shielded, then you have about 66% FracHit taking place, and the other simple ones are not on plane and shielded, and not on place and not shielded, and you can see the amount of FracHits are very, very low. So this is the highest possibility of actual FracHit, and the most often happens in actual fields in our industry. If you look at everywhere, that's so let's see the traditional technique that is used to make these models, how successful it is. So here's the case where it is on plane and shielded. And as you can see right here, it says, the conventional technique says there's no FracHit. So it is 100% not FracHit, 0% FracHit. And you can see it's actually wrong by 18%. And you come up to the next one, which is shielded, but it's not on plane. And you can see that again, the traditional technique says no, there's not going to be any FracHit. And as you can see, we'll be wrong about 5% of the time on FracHit, about 5% of the time when it's not FracHit. The next one is when it's not shielded and when it's no on plane, and in that case you can see that again, traditionally we say it's 100% no FracHit, and in reality you see 3% is FracHit, and that's the difference. And here is the actual one, the one that happens the most, and that is when it is on plane but it's not shielded. And as you can see, in reality we have 66% FracHit, whereby in our traditional technique says 100, all of them are going to have FracHit, and but 35% of them not going to get FracHit, and again it says 0% here. And that's where the traditional technique is most wrong, and where, as I mentioned, this is where it happens most of the time. So when you look at what happens in the traditional technique, the way it predicts it, the one that is most important, it is most wrong and cannot tell you what really happens. And in Shale Analytics, if we look at the same thing, as you can see, in this case, Shale Analytics says 11% when it was 17%, when it was 5%, it says 0%, and when it was 3%, it says 3% almost. The most important one is when it says it's 66% and FracHit by using Shale Analytics says 63%, and when it says it's 34% of the time you're not going to have a FracHit, it identified 37% of the time not being FracHit. As you can see here, when it is the most important, Shale Analytics does the best job in order to predict. And what I showed you was the work that was done by one of my grad students. The data was generated by him, Ryan Tyree, and the data is from there, but the analysis was that I showed you. I made the analysis Ryan made in his master's thesis can be shown here, and it clearly shows that the work that he did, the accuracy is much, much higher, but it's less than 1800 distance between the two. The industry standard give you about 70%, 76% correctness. Shale Analytics gives you 91% 100% correctness. When the distance between the parent and child is more than 1800, that's where the industry standard gives you about half the time is correct, and where Shale Analytics 94% of the time is correct. And this is the work that was done by Ryan Tyree, and the data that I used was data from his master's thesis. I just had a different type of analysis. The next one is fact-based dynamic modeling, and we used but a very large number of wells. As you can see, we built a purely data-driven numerical reservoir simulation. The data set potentially include a treasure trove of information. We had well location and trajectory, reservoir characteristics, well logs, core data, seismic attributes, completion data, hydraulic fracturing implementation, operational condition and production data. And the wells are in the same pad. The interference between wells are wells in the same pad and wells that are in the neighborhood pad. And again, that's the definition of we're talking about. The difference is that in the numerical reservoir simulation, you use a lot of soft data, hydraulic fracture, half length, width, height, conductivity. None of this really exists from a measurement point of view. Then stimulated reservoir volume. A lot of people use microseismic to do that. A lot of time there has been a lot of work done. If you read the papers and you find out it is 50-50 whether it's correct or wrong, and the SRV. In other words, all of these data, soft data, they're all assumed. Whereby the model that I'm going to show you, it's purely fact-based. It only uses the measured field measurement and what we call hard data. No assumptions made whatsoever, and you can see the. What you're looking at is the dots are the actual data, and the line is the top-down modeling, the TDM. You can see the history match, and this is the shade is the cum for both. You can see how close they are. This tells you the number of wells that we're producing. As you can increases, the production increases. When it stays the same, production decreases. And this shows you history matching of every single well, which actually that's what happened. We history match for every single well, then we sum them together for the entire. This is shown for the history match of this well. This is shown for this one. This is shown for this one, and you can clearly see that this fact-based modeling provides very highly accurate history matching without making any assumption whatsoever. With that shown, another thing that we do, we what we call blind validation. We remove, if we have the data from August 26 to March 2013. This was work done by one of my grad students, Sudhabe Smiley. I think she's currently working for Oxy. The data started from beginning to the end. What we did, we removed about 2 years, about a year of worth of data, and we built a model and history matched on the what you see here in the blue, and then we forecasted, and then we compared the forecasting with the data that we had to see how good it was. This is, you can see the result. The forecasting of the top-down modeling was very accurate compared to what we had in reality. This is for that. This was what you saw earlier was for the entire field. This is for specific wells, and as you can see, the forecasting is highly. And when for the history matching, about 106 wells had about 10% error, 23 wells had about 20% error, and so forth. For blind forecasting, again, you can see how low it was. And after it was done and finished, the company we had the data for provided Sudhabe with more data for new wells and asked them, can you predict? She did, and gave it to them, and this was the result. Again, these are completely blind. The dots are actual well. This is a single pad and multiple wells, and the model that Sudhabe made shows you the predictions, and the dots show you the accuracy. This is for another one. That completes this article. Thank you very much for listening, and if you have any question, I'll be happy to answer. Thank you.